Okay. But well, we are here with Roger Moore. In principle, he doesn't need any introduction, but of course, I will introduce him. Roger Moore is the head of the speech and hearing lab at the University of Sheffield. He has at least 40 years of experience in the field of speech processing and all the related matters. He has been awarded with a long list of prizes, the more important are the Zamboli Elrec Prize and the ISCA Medal for acquisition of results and research products in the speech of field. The ISCA Medal is something like the Turing Award for computer science or the Nobel for medicine, but the list of people that has achieved this award is very precious and interesting for the list of the names. And in 2025, Roger was awarded with this medal. We will discuss with him about mainly about speech technologies and speech recognition. And of course, we'll give also some views about other fields that are directly connected with speech recognition. The language we will use will be less technical as possible because the audience of this video will be mainly linguists without technological background or with a very few technological backgrounds. But if you want something more about this names about this concept that are involved in our discussion, we have prepared a tutorial that you will find on YouTube channel of the Società Italiana of Linguistics close to this video. So if you want, it's good for you to look at the tutorial before you go to look at this interview. Okay, Roger, welcome to Società Italiana di Linguistica.
Thank you,
And
Franklin.
we are very glad you accepted our interview. And so I will soon start with the first question. The first question is, we have seen a very rapid and abrupt changes in speech technologies in the interval between 2008 and 2016. Before 2008, we were still working with Markov models, language models based on n-grams or similar techniques. Now everything is changed, and now we have new technologies based on deep neural network and transformers, artificial intelligence. So the idea, the question I wish to ask you is, uh, what can be said about the older technologies that can be projected into the future, considering the new approaches?
Mm. No, we certainly have been living through an amazing revolution and somewhat surprising, but of course it's not entirely new. I mean, my lab way back in the 1980s were working on neural approaches, and a lot of other people were as well. So it's just that they have kind of in recent times overtaken some of the more traditional techniques in achieving amazing performance on standard test sets. So yeah, it's not like they just came from nowhere, but I guess what did take people with surprise was just how high the performance was. And it's not that the techniques are they're not really very insightful as you know as a algorithmic methodology compared to some of the more inspired modeling techniques we were using before, hidden Markov modeling and the like, which is based on some clear modeling principles about how speech might be constructed, and a clear mathematical approach to that. We seem to have discovered that by supplementing or replacing that kind of insight with masses of data, that we can overcome all those modeling limitations. And so the kind of models we have now are kind of rather simple in some sense. They're simply transforming one representation into another. But the difference is the just enormous amount of data. And of course, we also have much faster computers, so we can process the data. So it used to, there were people running running training their models for like 6 months back in 20, 30 years ago. So it's not surprising that didn't lead to any, much, but now you can do it in a couple of days. And so it's not that we have a deeper insight into what speech is like or how to model it. What we have is faster computers and a lot more data. And it turns out that that is good enough to create remarkably high performing speech technology, not just speech recognition, but speech synthesis, all aspects of speech processing have been affected by this.
But don't you miss the internal representation of a Markov model that was quite close, similar to the phonetic transcription? The new system maps directly audio into character,
Exactly.
orthographic character. So
Well,
we miss something now.
The question is who's missing it? The, and it turns out. So what I mean, the way the research developed was that the new approach, the neural approach, was applied to particular components, particular levels. So we had a model or a system before, an architecture before, with various stages. And so people were saying, well, maybe we could replace that stage with a neural architecture, and then maybe we can replace that stage with a neural architecture. And of course, what has been discovered with these so-called end-to-end systems is actually if you replace the whole lot, that's all you need because I mean, some of us had insight into this, but there were issues about the interfaces between the various stages that we had before. So although hidden Markov models had some very nice properties in terms of sequence modeling and links with phonetic structure and were configured that way, actually, the relationship between the signal processing and the hidden Markov models was not optimal in some sense. And likewise, the connection between the HMMs and the subsequent stages was not optimal.
Yeah. And another
But
drawback of this situation is that mostly it is owned by private companies. There is very few academic research in this field because we don't have enough data, we don't have enough computational power.
exactly,
It's a
yeah,
bit,
the whole dynamic has changed. So, in fact, it's not just about the fact that so much, that enormous amounts of data are very effective in training these systems, but um, it's the type of data as well. So this is no longer lab data. This is not something that some student has collected in an experiment. This is real. A lot of it's real user data.
Mhm.
So that means that the speech material that's going into these systems is highly pertinent to the use case
Yeah.
in which it's being used. But a point I, I want to make, and I often make, I mean, I inadvertently predicted this back in the 20 or more years ago now, because I was asking the question, and you may remember this, how much data is needed to get to an acceptable level of performance for speech recognition. And I did quite a lot of modeling of this to figure that out because at that time I was running a small company and we were trying to impact we were trying to put technology into mobile devices, which was a bit too early because actually there weren't many mobile devices around then. But that was our idea. But what I was worried about was alternative ways of doing things because even on a mobile device, you have pretty good visual interface.
Mhm.
And the question was, why would anybody want to use their voice? So I did some modeling.
Yeah.
And what I worked out was that in order, well, let me just backtrack slightly. A lot of people at that time, and probably still, talk about human performance,
Yeah.
how good humans are. And the assumption was, well, we've got to be as good as a human being, right? Or maybe even better, which seemed at the time a crazy idea.
Yeah.
Um, and I thought, well, that's not obvious that we have to be as good as a human. So as I did some modeling, and to shorten that story, the result that I figured out was you needed to have performance which was half as good as a human being, which is about on a general speech recognition task, that's
Yeah.
about a 5% word error rate. Human beings on average getting 2% or something like this.
Yeah.
We're not perfect.
Yeah, of
But,
course we are not. Okay,
but
then
the point was that the 5%. So the question I then asked is how much data do you need to train a system to get to that level?
yeah, I see.
And I have this famous graph which showed you need 80 lifetimes worth of speech.
Well, it's quite similar to what's happening now with the new systems. Okay,
Exactly, that's the point.
the present situation about the main technologies in speech recognition may be divided into three main groups. The first one is the still totally supervised system, in which, of course, you need couples of data that comes from the audio and you have to map them into the correct transcription. Then we have the partially supervised systems where huge massive amount of data have feed the system, and this data is being obtained by automatic transcription with the previous systems, which is system something that is not perfect, but the huge amount of data like in Whisper it happens, make it possible with very good results. And in the middle, there is the wonderful idea of a totally unsupervised system like WAV to WEC, which is quite suggestive for many reasons. So, what do you think about these three approaches? Which is the one you like more?
I don't like any of them. Look, okay, I mean, there's a difference here between what is practical, right? And most of my research and my interests are not directly aimed at coming up with the most, aimed at particular use cases. I'm very interested in the underlying principles and trying to understand what it is that you and I are doing when we're engaged in this kind of interaction and how we can understand that. And these models give no real insight into that process at all. From a practical point of view, yes, what you've just described is some really valuable insights into how you can use massive amounts of data and how you can sort of augment the data in automatic ways, which is a very practical thing to be doing. But thinking, I'm always thinking, well, in terms of what a child is doing, this is nothing like how human beings acquire these skills. Now, that may not matter, okay, airplanes don't flap their wings and all that. So let's not worry about that. But, uh, of course, it is possible to discover structure in a signal by um, comparing it with itself and just do sort of finding what emerges. I was involved in a European project some years ago, which was looking at these kinds of things and particularly trying to understand how it is that children form these first structures. And indeed, you can discover structure quite readily because it is a highly structured signal. But the relevance of that structure to the nature of interaction and communication, that's whole separate issue. That means that other sources of information need to be brought to bear. So you can't just self-organize meaningful structures and say, okay, that's it. Those are the fundamental components or units. These are terms I don't like to use at all. Um, of a signal like speech. They merely reflect repetitive patterns which may or may not have significance in the communicative structure of a conversational interaction. So, I mean, we discovered in that project that how important it was to go multimodal, for example, which is, I know, one of the things you're interested in. So, merely self-organizing from the acoustics, that gives you some insight into some of the patterning that's there. But if that's not done in the context of the relationship with what else is happening and with what can be seen in the environment and the nature of the interaction that's taking place, then it's not possible to measure the salience of the patterns that emerge from the self-organized structure.
Mhm.
So I think there's a conflict here between
Yes, of course.
what can be done practically, in order to efficiently get to an optimized system for a target use case, which is a very practical question,
Yeah.
that's an engineering problem, versus the science, which is what's going on under the hood here? How is this all working, and how does it relate to the system which we know works rather well?
Mhm. So, what do you, as far as you know, what are the mainly newest acquisition in studies about language acquisition in infants based on multimodal models?
Yeah, I haven't been following that closely in recent times because I've been much more involved in uh, interaction and communication, multimodal interaction with using robots.
Mhm.
But I there's a guy whose name I'm struggling to remember in Finland, Okko. I can't remember his surname. He's doing,
Okurazanen.
yes,
Okurazanen is him.
that's right. He's doing some fantastic work in that area, and he
Mhm.
was involved in our European project, and he's continued, and he's become quite a, I mean, he's somebody you might want to interview on
I'm
the.
sending him a PhD doctor for a visiting period in the next
Oh,
year.
okay, right, yeah. So he's doing great work, and so I occasionally look to see what he's doing, but I'm not
Mhm.
following that. I'm not following that area very, very closely anymore.
Okay, so let's move to something that involves speech recognition, but also dialogue systems. There is the deep differences between speech recognition and spoken language understanding. In all the system with dialogue, was way able to manage dialogues. We see that there always was a model that takes into account, into charge, the paper, the work of the understanding related to those things that speech recognition has provided. And nowadays, we see very often that this kind of module have been substituted by large language models, but we know that it doesn't work quite well. Which is your opinion for the future of language understanding more than recognition?
Uh, Well, that's also a very, I mean, a lot of these are very difficult questions. Looking into the future is really, really hard. But the, I think, I mean, that is a question which interests me greatly because I don't like to, so the traditional linguistic approach, tackling this through semantics and using that term understanding, um, there's a long history of research in that area. And now we're faced with these particular models. By the way, I don't like the term large language model because it kind of assumes that they somehow are modeling language, which I think they're not. What we have are large token predictors. And what is interesting about them is if you have an incredibly large token predictor, what is it? What are its properties? What can it do? And how does that relate to the structures that we know about in a signal like language? So uh, I have a rather sanguine view of how we use our terminology. We're very poor at labeling these things and then just confuse everybody.
Mhm.
So I come at understanding from the perspective of embodied and situated interaction. So I'm not a linguist. In fact, I'm sitting in a computer science department, but I'm not even a computer scientist. I'm a communication engineer by training. So my view on all of these problems is very mechanistic, and I'm interested in how those mechanisms function between living systems and the non-living world, and how do those interactions take place?
Mhm.
My view is that language is a sort of at the top of a pyramid of very interesting and complex interactive behaviors. And by studying language purely on its own, without appreciating that it takes place in the context of much richer interactive
Yeah.
set of behaviors.
There is always a big gap between the bottom-up procedure that comes from the audio signal and the top-down inference that comes from the knowledge representation. None of the module, the ideas that have been developed until now, create the correct link between audio and semantics in this, I think.
So I'm coming at it from, so it's not, to me, it's not a top-down versus bottom-up issue. This is more of a side issue, which is what is the relationship between linguistic style behavior and all other kinds of interactive behaviors? How do they fit together?
Mhm.
Language doesn't just sit on its own. Language is founded on other very sophisticated behaviors which we share with some of which we share with other animals.
Mhm.
So I don't know if you're aware, but I've kicked off a series of workshops on called VIHAR, vocal interactivity in and between humans, animals, and robots,
Yeah.
because there's a community of people who are very interested in the commonalities here. So not trying to look for special processes, which are unique, but to try and understand the general principles
Mhm.
on which the incredibly sophisticated behavior that we call language is founded, rather than just treating it as an isolated behavior, which is completely somehow self-contained and self-sufficient. My view is that it is grounded in real world interactive behavior, situated, embodied, and when we look at how kids acquire it, then we see all of that in operation. We see the kids actively exploring their physical and communicative world in order to create these incredible representations of everything that they are having to do as a living system.
Yeah. Okay, we are approaching to the end. I have just last two questions for you. The
Oh,
first one is there is a very old friend of mine. She's a computational linguistics and semanticist, and she makes fun of me because she says semantics has resolved any linguistic problem. While you're struggling with speech, you should try to move to other fields. So in some cases, I don't know how to answer to her to this question to this joke. I guess it's a joke, but what's your opinion? Do we still have something to do in speech sciences?
yes, absolutely. Because when right, so you say in speech science. So my assumption is that in the science of speech, we actually want to understand something rather than build a system that works. Right now, there's a ton of engineers out there building systems that work. They do things, and at least the performance is good enough for various use cases. We can argue about whether that's a good thing or not, but that's a whole separate question. But if you're talking about the science, then presumably we want to understand what's going on. Now that means that we're trying to understand this. We're trying to understand what you and I are doing right now. We're trying to understand how that behavior fits with respect to other behaviors. That's the point I was making just now. And there are many properties of the speech signal which are still not understood and not exploited on the engineering side, because a lot of the work that goes on there don't even appreciate that these things exist.
Mhm.
So if I just name an obvious example, that would be prosody. Right. So prosody has been studied for many years. What impact does any of that have on the current engineered systems? Very, very little. And even if they are sensitive to some of those properties, we don't know. So there's a lot of people kicking the tires of these engineered systems to see what they do. This is a rather strange thing, it seems to me, because in fact, summarizing where we've got to, we started off not understanding this system and had some simple engineering solutions. Now we've got this system we still don't understand, and we've got engineering systems we don't understand. So we can we
Yeah,
can now do science on two areas.
yeah,
So
yeah.
I think a lot of the original unknowns are still there. One of the features of speech which I'm particularly keen on and have been worked on for a number of years is Bjorn Lindblom's H&H hypothesis. You know about this, I'm
Yes,
sure.
of course. I love it.
Yeah. So I love this. The idea that, so for anybody who doesn't know, the H&H hypothesis is simply that articulation of speech ranges on a scale from hypoarticulation, which is like mumbling, minimum effort, through to hyperarticulation, which is maximum effort.
Mhm.
Now, this is not unique to speech. This is a fundamental behavior of all living systems. All living systems have to manage energy.
Mhm.
So if I gesture, I can make small gestures or I can make huge gestures.
Mhm.
That costs a lot of energy. That costs a little bit of
The
energy.
principle of economy, of course, yes.
Exactly. Now, that has a fundamental, I don't think it's just a neat idea. I think it has a fundamental impact on the way in which behavior is managed by living systems.
Yeah, yeah, yeah.
Where is any of that in any of our models? Nowhere.
I'm glad you talked about, you mentioned prosody, because I always struggled with the idea that speech contains a lot of information on different time scales and also on different level of interpretation, because from speech you can understand the prosody, you can understand the emotions, you can understand if I am a male or a female, which is my emotional state. So there is nothing of concrete in speech research that makes with one approach the idea of parallelizing all this level of information and analyzing them.
Well, yeah, it's not quite true. I mean, I have seen some really nice work using large token predictors, um, uh, where they do identify they specifically partition the architectures to capture some of those, to acknowledge some of those things exist, to either normalize them out or to explicitly accommodate them. I think that's some very interesting work. So in other words, putting structure into the what would otherwise be just
Who's
a
working on this? Who are the authors of these studies?
I see. I'm very bad at remembering names, as you've already seen. So I've seen some nice work on that in Edinburgh, because they do a lot of work on synthesis, and of
Mhm.
course, in synthesis, they're very interested in teasing out some of these different controls because they want independent control of individuality, of prosody. But by the way, going back, you just reminded me, going back to prosody, and your original question was about the link with semantics. Well, there it is. That
Yeah, of
that
course, yes. There is a lot of semantics in
that is
prosody.
how the true meaning of what is being said is hooked into the acoustics. And we don't have great models of this, and if we just take the view, well, let's just collect a lot of data and throw them at a large token predictor, then we're not going to learn much. We might find something that works quite well, but what are we going to learn?
So it means we have a lot still work to do. So we are not finished thinking and struggling.
I,
Okay, we are going to finish this interview. Just one question. Is there something that I didn't ask you that you would like I have asked to you for closing this interview?
Not really. I think I've managed to get in the situated embodied stuff, which is I noticed was not in your questions, and I wanted to make sure I mentioned that because that's mostly what I'm doing at the moment. We're working with
Something about. I'd like to know.
well, we're doing a lot of work with the fur hat robots. So I don't know if you know that one. It's a back projected face. And so I've got a bunch of students looking at how those interactions work. And one area which I've been working quite hard is on the uncanny. Do you know about the uncanny valley? And
Yeah, yeah, yeah.
so that interests me greatly because it essentially um, shows situations where communication breakdown occurs. And of course, what we want, and if we want to model this and come up with good solutions, we want the opposite of that. We want to avoid communication breakdown. So in order to avoid it, we need to know what it is.
Hmm.
And so I published a model of the uncanny valley, and subsequently we've been teasing it out and trying to figure out the implications of this model. And part of it, part of
Okay.
what the model is able to do is able to help you in if you're designing a communicative agent. It tells you lots of important things, which is, for example, don't stick a human voice on a big metal robot. People won't know how to talk to this thing.
Yeah, yeah.
So very interested in the idea of what it is to be a coherent communicative entity as opposed to a chimera of random speech recognizer, random speech synthesizer, random body, and then you throw that at a elderly a vulnerable user and say, this is going to be your companion.
Mhm.
That is absolutely awful way to proceed. So I'm trying to understand how we create entities which we can communicate with. And very keen to avoid anthropomorphizing and recreating people. We're not recreating people.
Yeah, of
This
course.
is where LLMs get into trouble. And you know, the press every day is full of people hypothesizing that they have all kinds of anthropomorphized properties when in fact all they are is large token predictors.
Okay, Roger, you have been very kind. I guess I think this chat with you was wonderful. So thank you again for accepting the interview. And if you allow me, I will look for your recent papers and I will link them into the video so people will be able to read your recent acquisition.
Okay.
Okay, thank you very much indeed, and thank
Okay,
you
Frank.
for
Very nice to see
accepting.
you.
Ciao.
Ciao.